Okay, this is the code. Try to generate a block of several block of with constant decay element. It's a modification of a Gary-Loft reliability model to simulate the lifespan. So my plan is to use log normal distribution to generate exponential rate for all the elements. I'm going to simulate the lifespan of each element, and the maximum lifespan of all the elements is the lifespan of each block. You can refer this to the figure 2 in Gary-Loft 2001 paper. The minimal lifespan of each block, the minimal block lifespan, is the lifespan of the system because each block is consecutively connected. And if one of them fail, that means the entire pathway will be blocked, so the system also fail. And so for the simulation, I basically simulated the every system lifespan and repeat for all systems, and that means individuals in a population. Okay, so first I'll give you a function to calculate the S and M. S is the viability, M is the mortality. And let's take this function as it is right now. So I assume there are n number of elements in each block. There are m number of blocks in the system, in a system. And for this simulation, I will generate n POP number of individuals in a population. So to generate the random decay rate, I assume the mean decay rate is 0.1, and then I'm going to try different standard deviation to see how the noise contributes to the simulation result. The noise will increase from 0.1 to 1.5. That's a standard deviation. So so I'm going to first run over do the simulation for every standard deviation. That's different noise. That's a SD loop. And then for each loop, I'm going to simulate a population. Now, to start that, I need to generate some empty buffers vector to store the simulation result. So that will be something I call the system age. It's basically the lifespan for each individual in the population. This will store the lifespan for all individuals. The block lifespan is basically a buffer. I don't need to store the block, but I need this one for the simulation. For the for loop, I need something called block age. So it's just a temporary buffer for temporary storage. And now I studied the individual loop. So each I indicates the ith individual in the population. That means ith individual in the population. And then generate a mu vector, which is store the constant failure rate of element. I'm not sure whether mu vector should be inside of this individual loop or outside of it, but it seems to inside give more better result. I didn't do quantitative check, but that seemed to be the seemingly that's the case. Yeah. And then I use a J loop to simulate the lifespan for every block. And for every block, I generate all the element lifespan. using the exponential random variable generator. R for random variable, exp for exponential. So there are n number of elements in each block. So I generate n number of exponential variables for every element. Those are the element ages. Those are the element ages. That's the element ages there. And I then take the maximum number of all the element ages. The maximal age for each element is the age for this block. Okay, we all agree on that. And I rounded this number to the 0.1, so the first decimal point. And then I call that block ages. So I rounded all them to 0.1, last one decimal point. And then I calculate the minimum of that block age. For every block, I give you the age. Because all the blocks are sequentially connected. So if one of the block fails, that means this entire system fails. So the minimal age for the blocks is the age of the system. Are we good on this? Okay, because all the blocks are sequentially connected. So for the system function, you can imagine this is the electricity pathway. Electricity has to go from this end to this end. But if, say, this block malfunction is stopped functioning, so the electricity cannot pass from this end to the right end.
So the minimal lifespan of that failed block is the lifespan of the system.
Correct. Yeah.
Okay.
So basically, the minimum any block fails. The first block fail is the minimum age. I don't care which block fail, as long as one of them fail, that system fail. This is a sequential system. But for every block, the element is in parallel. It's redundant.
Yeah,
so yeah.
Still, even if one of the individuals died, that block can still live.
Yes. So in fact, as long as one of them lives, the block still functions. So the maximum of the element is the lifespan of the block. But the minimum of the block lifespan is the system age. It's a little bit, yeah, okay. Basically, here's the code trying to do here. So the minimal block, and then I simulate everything and calculate the lifespan mortality rate. Okay, I need to stop this.